The heart of a servo-hydraulic system is the servo valve. So in this class or this video lecture, we're going to talk about how this servo valve works in a little bit more detail. So let's do this in building blocks. Let's first of all start off with our prior discussion of a directional control valve. So this will be a manually actuated directional control valve. And if you recall, my manual actuation of this lever is shifting the spool back and forth, and doing so will change the porting of this valve. So as I do this, I'm going to be connecting my pressure to the A port here, and then the B back to the tank port. And again, the purpose for this might be that I have, let's say, a hydraulic cylinder up here, and let me draw that rod a little bit better, and then I'll be connecting the A to the cap side and the B to the rod side, and this would allow me to control that cylinder. So this was the most basic that we could have for a directional control valve. And then we said, well, we can actuate this in a variety of ways. It doesn't have to be manually controlled. One option is that we can make it a directional control valve with a solenoid. So this valve right here has two solenoids that will move the valve back and forth between its positions. And going to a solenoid operated valve or some sort of solenoid-based system, first of all, it's very simple, relatively inexpensive, but it does not allow us to go up to very high frequencies, especially with high flow rates. So you can imagine to go to higher and higher flow rates, what do I need to do? Well, I need a larger spool. And a larger spool has more mass, and to drive this mass back and forth at a high frequency, I need a large amount of force from the electromagnetic circuit. And we can only get solenoids that are so big. So we're kind of limited in how fast we can drive this. So another option is to say, what if I take that same spool and instead of driving it either manually or with a solenoid, what if I drive it hydraulically? And so I have another valve, a first stage, that is controlling this second stage. So it might look something like this, where this would be the second stage valve, and this is what's really doing the work, or what's going to be controlling my hydraulic circuit. And what I want to do is apply pressure to the two sides of this spool, so I could say have a P high on this side, and perhaps on this side have P low. And doing so would then drive this spool to the right and allow me to have my flow paths from my pressure port to the B port in this case, and then the return flow from A to T in this case. So this just shifts my valve, but now I'm controlling it hydraulically. So this would then be a second stage, and I need a first stage to drive this. Well, this is taking me towards what we call a servo valve. And this is a servo valve right here. The type that we're going to talk about today is a flapper and nozzle style. There's also other styles as well, but this is the most common style, and I have it diagrammed here. Now, what's really the heart of controlling this is what we refer to as the torque motor. So the torque motor is up on top here, and first of all, let me diagram what this torque motor is reacting against. So there's a permanent magnet which then causes these pole pieces to be magnetized. So let's say that this is the northern pole of the pole pieces, and then this would be the south pole. And then what we're going to do is we're going to send a current through this coil that's wrapped around the armature of my torque motor. And as I send a current through it, whether or not it's positive or negative, I can magnetize this and basically say, all right, let me make this pole north and this pole south of my armature. So this is what the electromagnet is doing. And you can imagine that the current that we apply is going to change that magnetic field and therefore change what the torque is that this motor is exerting. Hence it's called a torque motor. And it primarily pivots about its center right here. So what happens when we apply a torque to this? Well, what it does is it rotates and it then causes this flapper to partially block this nozzle. So it creates a restriction. Let me back up a little bit onto this hydraulic circuit so that we can better understand this. So I've got the large pressure area that I have as P's down here, and you'll notice that there are some fixed orifices. So these are just machined orifices. I've got one on the left side here, one on the right side, and that is to then the cavity or the space that is on either side of the spool. I then have a second orifice, which is now a variable one, which is the nozzle to the flapper. And so you can see that right now my flapper is very close to the left nozzle, and so I'm going to be building pressure on this side, so my area is low right here, the area of that orifice, and the area of this nozzle is going to be high. Well, what's that going to do? It's going to create high pressure on the left side, low pressure on the right side, and therefore will drive my spool to the right side of the valve. So this first stage is driving the second stage of the valve. This torque motor because there's not a lot of inertia to it, I can actuate it very quickly so I can get very fast response from it. It allows me, very high frequency behavior, but then it's controlling this hydraulically so we get the force amplification of the hydraulic system. Now, this isn't enough yet. We need to somehow add some feedback from the second stage back to the first stage. And the way we do that, you'll notice that there is a ball right here that is in a groove in the main spool. And this ball is attached to what's called the feedback wire. And this feedback wire is basically a beam spring. And so as the spool shifts to the right, as it has right now, it causes that beam spring to deflect. And you'll notice now that this beam spring is creating a torque on the armature. And this torque is then reacting the torque that's being created by the electromagnetic field. When these two are in balance, then the flapper is going to be dead center between the two nozzles, and we're going to have the same pressure on both sides of our spool, so our spool will stay in that position. If I increase the current going to the torque motor, it will deflect that slightly more and I'll move my spool more, or if I drop the current, it will shift back a little bit towards center. So this provides mechanical feedback from the second stage back to the first stage. So we've got a few cascading gains in this system. So the first gain is that I have a current going to my torque motor and the current is proportional to the torque. The next is that my torque is proportional to the spool position. One step farther is that we can say the spool position creates an open area of the valve, and we know that the flow rate through a valve is proportional to the area. So at the end of the day, we can say that the flow rate is proportional to the current being sent to this servo valve. So this makes this great to control because if we want a desired flow rate, all I have to do is send it a current. And it makes it a very high performing valve, very fast due to this, the low inertia of the first stage, but allows us to have relatively high flow rates for that second stage and do that with closed mechanical control, first stage to second stage. So a very powerful valve, quite a bit of capability here. So let's look at what these components actually look like inside of this servo valve. So this servo valve, the same model, is disassembled, and you can see the components here, and you can see them referenced to a penny. These components are really quite small. So you can see the main spool with its metering edges. These are very precise metering edges that are what's called critically lapped or very close to critically lapped, which means that at the moment that the pressure to A port is closing, the pressure to B port starts to open. So a critically lapped valve makes it very expensive to manufacture. You might also see that tubular piece and the disc-shaped piece. Those are both filters. We have very small clearances in a servo valve, and because of that, filtration is very important. We don't want to get any small grit into these nozzles or other parts of the valve because they'll cause it to be sticky or otherwise lag in behavior. So filtration and cleanliness is really key whenever you're setting up a servo hydraulic system. You'll also see the torque motor with the needle and the armature assembly. Fairly simple components, but when you start putting them together and make it very high precision, this becomes a quite expensive valve, but it offers performance that there's no way we could do with a solenoid operated valve. All right, so we're now going to take a field trip and talk about what we can do to increase the flow rate even further beyond this two-stage valve if we need higher flow rate. And here we're going to add an additional stage and go to a three-stage valve. So sometimes with servo hydraulic systems, we want to control very large forces or large actuators. Well, when we do that, we're going to find that we have some limitations in our two-stage valve. Well, we've got a spool size that's kind of a uniform size, and if we start to increase that spool size, what happens is we need more flow rate from the first stage to drive it, which means we need a larger torque motor, and then we add more inertia to the torque motor, therefore we need higher currents, and it just starts to respond slower. So we're kind of stuck as to what the maximum frequency that we can achieve with this given spool size. We don't really want to make it much bigger. So one option to increase the flow rate coming out of the valve is we can add a third stage such as this. And in this case, our two-stage standard valve that we've been talking about so far will now, instead of feeding an actuator directly, the flow coming out of this will go to this third stage of the valve. And so now you can see that this third stage, this is what actually is supplying the flow to our actuator. So the flow coming out of our servo valve is porting to either side of this, and that is providing the flow forces to drive this third stage valve. Now, you remember in the two-stage valve, we have mechanical feedback from the second stage back to the first stage. Well, we don't have that when we go to this third stage, from the third back to the second and back to the first. And so what we do here is we add an electronic feedback through a position sensor. And our position sensor is an LVDT on this side, and you can see the core of the LVDT moving back and forth here. So that's how we provide position feedback that we use in our closed-loop control of that third stage. So again, adding this additional stage allows us to go to higher flow rates, but still maintain the very fast response we want from a servo-hydraulic system. So if that three-stage valve that we just looked at is not sufficient for flow rate, so we took first stage, added to second, put that on top of another stage with LVDT position feedback. If that's not sufficient, we can go one step farther, and this would be a four-stage servo valve. So now we actually have closed-loop control now through an LVDT to the third stage like you just saw. We then add that to another stage, or the fourth stage, and this valve right here has a rated flow rate of 15,000 liters per minute. Now, just to quickly do a back of the envelope kind of calculation on this, if we've got a flow rate of 0.25 cubic meters per second, which is 15,000 liters per second, and I multiply that by a standard industrial hydraulic pressure of 21 megapascals, this ends up being a power of about 5.25 megawatts. So enormous power capabilities for a very short amount of time through this type of a servo valve. So we can say, yeah, servo valves are slightly limited in their flow capabilities for a two-stage valve. We can then go to a third stage to add more flow capability, or we can keep going and add this fourth stage and still have very high dynamic performance or fast dynamic performance from such a large valve. So pretty impressive power and capabilities from this system. So as a summary, we've talked about how servo valve works. And again, we have a torque motor up in the first stage, and then that is driving the second stage through a nozzle and flapper where we're providing pressure to one side or the other of the spool. We have mechanical feedback from the beam spring that's going back to the torque motor. And this allows us to have very fast control of the valve, but still have very precise positioning of the spool. So it allows us to have a very precise, very high performance valve.